Hello, I'm delighted today to be joined by someone I admire greatly and have had the pleasure of working with a couple of times over the last few years, Professor Simon Conway-Morris from Cambridge University. He's Professor of Paleobiology and he's a Fellow of St John's College. And he's someone who I consider to be one of the most inspirational evolutionary biologists on the world and certainly of my lifetime. Professor, it's great to join you today. How are you doing?
Very well, thank you, Sam, and I'm glad to be able to talk to you.
Excellent. I've really enjoyed your books, and I've often given them to my students when encouraging them to study ancient life. Why don't you tell us, for those who are a bit unfamiliar, a bit about your background?
Well, I was born in London, in Wimbledon or Rains Park, depending on your sort of social scale, and went to King's School, Wimbledon, and ultimately to Bristol University, where I studied geology. And I was very happy in Bristol. In fact, I met my wife there, apart from anything else. And when I was in Bristol, I had a very inspirational teacher, Crosby Matthews. I was well taught there, in any case. And for some reason or other, in passing, perhaps, he mentioned that there was a project in Cambridge under the direction of a chap called Harry Whittington, and it was on the Burgess Shale, which, of course, I'd never heard of. And the Burgess Shale is, in fact, a series of sediments from Canada. And the remarkable thing about these is that they contain not only the ordinary Cambrian fossils like trilobites, but also, almost unbelievably, soft-bodied remains. So in due course, and perhaps by a set of fluke circumstances, I ended up starting my PhD in Cambridge. Of course, as soon as I arrived in Cambridge, I got appendicitis, but after that, things settled down. And I was able to devote many years, first as a PhD student, and then subsequently as a research fellow in St John's. And then I moved to the Open University for a few years, came back to Cambridge. And since then, my interests, I believe, have expanded way beyond the Burgess Shale. But that's the beginning of my life, if you like.
It's amazing the number of guests we have on here who quote an inspirational teacher as being a big part of what drove them, what got them into their field. But it's interesting you note that you started in geology. Was young Simon Conway-Morris picking up rocks in Wimbledon and examining them under a magnifying glass?
Well, the extent of discovery there was, in fact, an enormous hole at the end of the garden, and actually almost by a fluke, because it's basically river gravels there. In fact, I did find a sea urchin preserved in flint, which I still possess. And for me, it was a sort of moment of immense excitement. I was probably about 10 at the age, but at that time, and as a teenager, I and especially another friend called Michael Bishop spent a lot of time collecting fossils. It's partly on the Dorset coast, as you might imagine, but also in France. And my parents were very sort of patient. And although I went to do geology, because of course I'm fascinated in all aspects of science, I was, so far as I could be, determined to become a paleontologist, and that was my heart's desire.
Did dinosaurs factor into this at all? It's that's usually quite a common thread, or was it sort of creatures that were much older than that?
Well, it wasn't really dinosaurs. The only dinosaurs I had looked at very closely indeed came at the bottom of cereal packets in little plastic forms. And for some reason, unlike just about every other school child and schoolgirl through the nation, I can see why they're so fascinating. And of course, I have read a bit about them, especially how some of them transform themselves into birds, for example. But no, nevertheless, it was more just, I mean, collecting fossils per se. And I have to say, in comparison to my friends when we went collecting, I was singularly hopeless. I'd walk past a magnificent specimen, almost trip over it, and the chap behind me would say, "Oh, what's this here?" So I didn't take much credit for that. But by and large, I suppose, anything you could hoik out of a rock. So mostly, of course, at that stage of life, it was ammonites, belemnites, sea urchins, that sort of thing. And occasionally vertebrates. We used to collect a lot around Bedford. Went into quarries, which you must not do. It's very dangerous.
Yes.
Thank you. And found bits of ichthyosaur, things like that. So the odd piece of vertebrate. No dinosaurs.
Yes, and I immediately in my mind am jumping to the famous line from Darwin about endless forms most beautiful. So were you just captivated by the kinds of things you found and the mystery of ancient life?
I think I was, because at school I excelled, if that's the right word, in biology. I was moderately good at chemistry. And again, I must perhaps encourage a few of your listeners. I failed A-level physics. Actually, I've got 2 O-levels in physics, but I don't have time to explain that. So I'm not very numerate, I'm afraid. I should also add to that, that's very much to my detriment. I wish I was more numerate. But that said, I was always fascinated in living forms as well. And I suppose going almost full circle to the Burgess Shale, where you have this soft part preservation, you really need a zoological knowledge to understand them. And I think in that sense, given my teaching at school and then to some extent in the first year in Bristol, I had a great advantage.
So you end up spending some time in Canada at the Burgess Shale and become something of an authority on that. Could you tell us a bit more about the sort of things you were doing out there, examining the Burgess Shale?
I beg your pardon. It wasn't quite like that. Oddly enough, I've just come back from Canada, where I've been looking at some remarkable fossil fish from the Burgess Shale. But at that stage, as it turned out, almost the entire collection which was available was in the Smithsonian Institution in Washington, D.C. Now, the Canadians had reopened the quarries which had originally been discovered by Charles Walcott, an American geologist, before the First World War. And they made collections in the late 60s when I was still at school. And as I mentioned a moment ago, Professor Harry Whittington, who became my supervisor, in fact, at that stage was in Harvard. And although he was English, he was thoroughly an American. But for various reasons, he was minded to accept the so-called Woodwardian professorship in Cambridge. I won't go into the reasons why he did, but I think he was glad at that stage to leave Harvard. In any case, had he not come to Cambridge, then some bright student in Harvard would have got a project on the Burgess Shale, and it would not have been Simon Conway-Morris. So hence, when I met Harry Whittington and then we agreed on a project and so forth, although there were some collections from the Canadian exploration, the great bulk of material was in the Smithsonian. So for those years, I spent a lot of time going to Washington, D.C., which actually was also good fun in all sorts of ways. It was more or less my first real experience of America, a country I like very much indeed. And thereafter, many other things happened. The Royal Ontario Museum in Toronto, where I was last week, started a major campaign and now have many, many more specimens of the Burgess Shale than the Smithsonian. So altogether, to a scientist, there might be, 300,000 specimens available. Pretty good.
Excellent. So what was the main body of your PhD research?
Well, it had an extremely exciting title. It was entitled The Worms of the Burgess Shale, heaven help us. And actually, all that was more or less a sort of dustbin group, in as much as the bulk of the Cambrian faunas, both in things like trilobites, which are familiar, and in the Burgess Shale, are the group we call the arthropods, which today we are familiar from crayfish and flies and centipedes and those sorts of things. There's a whole medley of other forms, which include worms which are fairly familiar to most zoologists, things like the polychaete worms, which are related to the earthworm. There are other ones which are less familiar, entirely marine, called the priarpulids, and then a rag bag of other things. And it turned out, in fact, that one of the animals I looked at looked so weird that we gave it the name hallucigenia. And this is a very useful sort of cautionary tale for all scientists, because I got my interpretation fairly accurate with one slight exception, and that is I reconstructed the animal upside down, which is not exactly a career move to be recommended. And in the fullness of time, it turned out that hallucigenia, although it still looks pretty weird, is actually a primitive arthropod. So I did dabble my toes unwittingly in the arthropods. But there are a whole variety of forms there, of which the polychaete worms were perhaps the most beautiful, the priarpulid worms perhaps the most interesting, and then a medley of other forms, which in many cases were only known from single specimens. They were very rare, and I think I probably did as well as I could. But since then, other people have actually greatly refined and extended our understanding of these. And that too, as a scientist, is very much what one should expect, but also not be embarrassed about that. Everything is work in progress. And a couple of things I got, I think, pretty well right, but quite a few other things really either needed major modification or were quite simply wrong.
Hmm. And when I think of polychaete worms, I think of them sort of in the deep ocean. And they do thrive very much on Earth today, a lot in some extreme environments. So this is a case of studying ancient life that is still very much present on Earth, isn't it?
Very much so. In fact, if you go down to the seashore with a little bit of fosking around you, well, for instance, you see those little castings of mud on a sandy shore. Well, they're made by one sort of polychaete, arenicola, and then if you break apart the rocks, then quite often you'll find so-called ragworms. And the like, but indeed I beg your pardon, they extend to really almost, I think, all ocean depths. But they're a major component. And you mentioned a moment ago about endless forms most beautiful. Well, the variety of forms, including ones which actually are what we call pelagic, that is, they swim. And amongst those, and this almost segues into one of my great interests in science, amongst these is a group called the Alciopids, and they have eyes, that's quite common in zoology, but actually they have eyes which are remarkably similar to the eyes which you and I are using, the so-called camera eye. But we can show beyond reasonable doubt, and more convincingly still when we look at the octopus or the squid, that such camera eyes have evolved independently a number of times. And this is what we refer to as convergent evolution.
Mm. Yes, something that you're very well known for. But before we get into that, I'd love to hear about some of the other places you've been. Could you tell us a bit about other countries you've been to and other sites you've visited?
With respect to Burgess Shale, the thing I enjoyed the most, I suppose, was I was very lucky to be able to join a colleague called John Peel, who's now in Uppsala in Sweden, but at that stage was in the Greenland Geological Survey. And people mapping the geology in the far north of Greenland, Peary Land, found some fossils. And then when John looked at them later in the lab, he realized that there were actually Burgess Shale type fossils there. And he showed them to me, and I said, yes, that's right. And we got a paper out on that. There weren't many. And he arranged actually what turned into 3 expeditions. And I can't go into all the details, but it's quite adventurous. You're put in on a thing called a twin otter aircraft, and you camp there, and you're 300 or 400 miles from any sort of help. It's tundra. It can snow in July, and so on and so forth. And we found some wonderful fossils in a fairly small locality. One of them was an animal known as a halkierid, which needn't detain us too much, but my opinion, though not shared by everybody, actually is these halkierids have a close link to a number of the other Burgess Shale fossils, which I studied some years beforehand. In addition to that, I've also done quite a lot of work in China on Burgess Shale-like fossils, working with colleagues in Xi'an. And I've done a little bit of field work on the Burgess Shale localities, nothing very extensive, but I have done quite a lot of traveling around China in the past, collecting other fossils of much the same age as the Burgess Shale, but tiny skeletal remains, which in the end have connections to the Burgess Shale, but that's in a sense a different story.
And you mentioned age. This is Cambrian, is it?
That's correct, yes.
Yes. So tell us a little bit about Cambrian life.
Well, the Cambrian, let us say, just you know, in everybody's layman terms, is let us say it's about 530 million years ago. So it's ancient on a human perspective, but in terms of the history of the Earth, which extends back to 4.6 billion years, actually it's relatively young. And when the Cambrian faunas were first being described, not least by a former Woodwardian professor in Cambridge known as Adam Sedgwick, a remarkable man who, apart from anything else, knew Charles Darwin when Darwin was a young man in Cambridge. And almost anywhere you go in the world, just on a day-to-day basis, you can find these in Wales, of course, and any other Cambrian locality you care to mention. The fossils you find are usually in some abundance trilobites, usually quite a lot of brachiopods, usually some sponges, and these of course all have hard parts which preserve relatively easily. And then there are a few add-on groups there which are generally rather more rare, maybe some mollusks and a few other things, you know. But so the point about all these sort of things is that those are exactly the same sort of groups you find in the Burgess Shale. except, of course, in the Burgess Shale, in terms of numbers of individuals or numbers of species, they don't account for much more than 5 or maybe 10% of the total. So the great thing about deposits like the Burgess Shale is that they open a window, still narrow, I grant you, but in the order of maybe 90% of things which otherwise you would never ever see in the fossil record, because they're effectively soft-bodied and therefore would decay within a few weeks. And that in turn begs the question, how on earth did they come to be preserved? And that too has been investigated widely, but still I don't think there's a completely satisfactory explanation yet.
Hmm. And you detail much of this in your book, The Crucible of Creation, which I read when I was an undergraduate, which really goes into that extraordinary life, because this is commonly referred to as the Cambrian explosion, isn't it? There's a great diversity of life. Why do you think all these endless forms, most beautiful, just really exploded during the Cambrian?
Well, in a sense, we go back, in fact, to Darwin and Sedgwick, and Darwin actually refers to this in The Origin of Species, although at that time the understanding of global stratigraphy was somewhat rudimentary, but it was self-evident that the great thicknesses of ancient rock were devoid for all intents and purposes of fossils, and then skeletal remains, as I mentioned a moment ago, seem to appear not overnight, but quite abruptly. And I've seen this, for instance, in sections in Australia. It's really quite striking. You're going up one of these dry gullies, and the sediments, have got lots of nice things to look at, but not much in the way of obvious skeletal remains. And then the skeletons suddenly pour in. But as ever, of course, the question is, because Darwin demonstrated evolutionary continuity, it so turns out that before the Cambrian, there's a late stage of the so-called Precambrian, or Proterozoic, if you prefer, which contains a very interesting assemblage of fossils which are referred to as the Ediacaran. And these two have a global distribution. And again, there's another paradox here, because these things are, for all intents and purposes, more or less soft-bodied, yet they don't occur in the same sort of way, by and large, as the Burgess Shale. Well, it's not easy to unpack all this, but there's been a great deal of debate over many years, but it's now pretty clear that these Ediacaran fossils are animals, and it's also, to some extent, less clear, but they have some connection with the Cambrian faunas, including Burgess Shale types. So, in fact, what you're doing is you're extending the history of animals tens of millions of years beforehand. So, although it's an explosion, it's really an explosion of skeletons. And that's what's most obvious, because that's normally what survives. But even so, it does beg questions as to what's happening as the planet changes. And I'm not up to speed in this area at all. I've been much diverted in other topics in the last few years. But my understanding is that one thing which may have changed quite dramatically was the nature of the oceans, and especially the degree to which they were mixed as against stagnant, the amount of oxygen which was present in the oceans, and so forth. And these may well have, if you like, lifted a lid, so that once the lid is lifted, then in the classic way which Darwin described, so evolution gets underway.
Yes, I'd heard that, and I was going to ask you if that was sort of an active area of research today. We're very fortunate. I work at the University of Reading part-time, and in our new Health and Life Sciences building, we've got a small museum, and we have a number of Cambrian, but also Precambrian and Ediacaran fossils there, which is a great place to take your children and just introduce them to ancient life. But yes, I had always suspected that perhaps there were some serious changes to the planet that helped allow as you put it, lift the lid to allow this to happen. So this is really where geology and earth sciences and evolutionary biology intersect, isn't it?
It is indeed, yes. And again, one could sound very facile here, but I suppose I've been very lucky. But apart from my sort of lamentable lack of numeracy, I've always been interested in trying to join the dots, as we say, and also seeking analogies. So things which appear not to be able to be relevant in any way to one another actually seem to have an intellectual connection, if you like. I mean, it's a little bit unfair, but I had a correspondence recently with a colleague elsewhere, and he was mentioning a particular categorization. And I said, actually, this is actually exactly the same as what Thomas Aquinas defines the different sorts of soul. Now, we don't have to get diverted into that. It's simply to remind oneself that quite often you'll find at the least similarities between apparently unrelated areas. He, I must say, in his reply was deeply unimpressed, but that's by the by. But the thing there is, and I think especially in geology, I was once told a story, I don't know whether it's true or not, but in the Second World War, when the Americans were trying to track the Japanese submarines, which of course the Pacific's quite large and the submarines are quite small, and obviously there are things you know about submarines where you can have some degree of predictability. But I was told once upon a time that actually people who had a geological training seemed to be rather good at sort of guessing where the submarines might be. So in a way, geology is an interesting subject because when you look at a mountain or something like that, and try and make sense of it and bring together information, which it might include fossils. I'm not going to exaggerate this, but it's a science which is probably more reliant on imperfect data than perhaps chemistry and physics are. So in a certain sense, it's softer, and also it's perhaps on occasion more frustrating. But on the other hand, the great advantage, which I learned, I suppose, originally in Bristol, when I did my geology there, is how one can learn how igneous petrology and structural geology and paleontology, although they're not related, there's a way of thinking there, which I think is really an advantage. Excuse me, sorry.
Yes, yeah, and interdisciplinary now, particularly when we look at things like genetics as well, is really informing evolutionary biology. I remember when I started as an undergraduate, I was warned by one of my professors that evolutionary biology was currently the fastest growing science because of all these interdisciplinary aspects. But I'd love to get to another book you wrote called Life Solution. Which is all around convergent evolution and something you're known very well for. It's a terrific book. I've given it to students who are interested in evolutionary biology. So for the uninformed, could you just break down what is convergent evolution?
It's the observation that in some sense or other, from different starting points in what we call a tree of life, and I could actually, if you gave me a moment, wander across and fish out my copy of Darwin's Origin and show you the figure right at the end, but you can find it on the web very easily. And what it shows is a set of continuous, diversifications. And Darwin, I think, was mostly interested in animals and plants getting more and more different. Excuse me, I beg your pardon.
That's right.
And that he only touches on convergence sort of really just in passing. And I think there are various reasons for that, which we might unpack if we've got enough time. But when you look at the various evolutionary outcomes, you find that again and again and again, effectively the same arrangement has evolved more or less independently. Now, there are various sort of cautionary notes here, but I mentioned, I think, a few minutes ago about the fact that polychaete worm and ourselves as vertebrates, and also the group which includes the squid and the octopus, all possess a camera eye. Now, these camera eyes are effectively arranged in the form of two chambers with a lens in between and a retina at the back. And when you look in detail, especially if you compare the eye of the squid and the eye of the human, actually they're not identical. And that's not surprising because each has had its own evolutionary history. But if you hold the textbook 3 feet away, they look almost indistinguishable because they're doing the same thing. They're focusing light in particular ways. And there's a trick here because looking underwater is not quite the same as looking in air. So we have to make other sort of adjustments to that sort of story. But the net result is that the squid, as it so turns out, and this is something which is really only clearly established on the basis of molecular biology, which you mentioned, Sam, a moment ago, is actually very closely related to the earthworm. So there we go. And for those of you who like not long words, squid and earthworm and various other groups belong to the so-called Lophotrochozoans. In contrast, we are chordates and vertebrates, and our closest relatives are, as it happens, starfish. There we go. That's the way it is. So we can show beyond reasonable doubt that if we assume all animals have a single ancestor, and even that is not quite clear, they may have two, but that's a different story, then the animal in question would have probably sensed light, but at a most primitive level, with nothing like the sophistication of the so-called camera eye. And thereby, this independent evolution of the camera eye is an example of convergent evolution. And then there's a squeal of brakes. And people lean forward and say, you're not being fair, Simon. You're not telling them about the genetics of eye formation. And it is indeed the case, to the first approximation, that the same genes are used to make the squid eye as our eye. And this includes a thing known as PAX6. Well, actually, that's not fatal to the argument, inasmuch as it's pretty clear that PAX6 originally is involved with the evolution of brains. It's not involved with the evolution of eyes. It's been recruited for the evolution of eyes because, of course, an eye has to have a connection to the brain. So although some people would say that there's a deep similarity, what we call homology, I'm much more impressed, if you like, by the engineering of these eyes. And this persuades me that they're convergent. And then in Light Solution, and even at greater length in a later book called The Runes of Evolution, and if you say that very quickly, it's ruins of evolution, never mind, then I can give you examples of evolutionary convergence which involve social systems, dolphins and chimpanzees, or I can give you examples of molecular convergence, and I could give you an example of an enzyme known as carbonic anhydrase, which has evolved independently for no clear reason at least 3 times and probably 8 times. And we can show beyond reasonable doubt that these are independent, but they function in the same way because they have to do the same thing. Carbonic anhydrase involves the exchange of carbon dioxide and water. Camera eyes involve vision.
Yes, and in my own work, I see evolutionary convergence a lot in genes, molecules, cells, like the immune system, for example, as well as DNA repair proteins. One very famous example, I mean, you've mentioned eyes, but another one people point to is flight. So flight obviously showing up in dinosaurs, birds, insects, and then in a rudimentary form in some flying squirrels and obviously bats. So is this a case then that nature just seems to find certain avenues of success, and so they show up over and over again because they're useful?
Yes, it seems to be that way. I mean, on occasion, and this is words used by other people, not just me, they say that there seems to be, if you like, a sort of an attractor, that things seem to navigate, if you like, through geological time to these particular solutions. And it's not, of course, that everybody's got to have a camera eye, for example, because, of course, there are actually probably about 40 different sorts of eye, of which the most common alternative to our camera eye is the so-called compound eye. But a compound eye has also evolved independently, I think at least 4 times, possibly more than that. So, yes, the idea in the end is that if you think about the possible number of combinations in biology, it turns out that, you know, the number is stupidly, staggeringly large. It's again, my limited understanding of mathematics is that when you're dealing with orders of magnitude, 10 to the 90 is quite a big number, and that's, I'm told, roughly the number of particles in the visible universe. So that's a fairly hefty number. But actually, if I talk about 10 to the 120, that dwarfs 10 to the 90. And when I talk about biological alternatives, which perhaps in certain cases are 10 to the 200, the immensity of this space is so titanic that the likelihood of ending up in the same place is basically impossible. However, if it turns out that practically every alternative you care to mention just doesn't work, because in the real world, which exists, they simply don't function, then it may be that although one has in principle an enormously large space to play with, and this of course segues into the possibilities of extraterrestrial life as well, are they radically different, or are they perhaps suspiciously similar to what we find on this planet? Then it may be that although indeed in life there are tens of thousands, maybe even millions of alternatives, that's a drop in the ocean compared with the number of all potential possibilities. And then you can think of, or at least hint at, the idea that in the same way as physics depends on underlying structures which manifest themselves at other levels, that maybe in biology also there's, if you like, an underlying template of organization. And this actually goes back in a sort of way to the ideas of a man called Richard Owen, who was a contemporary of Charles Darwin. But although he accepted evolution, he had no trouble with that. He didn't really think that Darwin's formulation was actually the correct one. And he didn't articulate it in a particularly clever way, but then neither can I. It's almost an intuition at the moment. Although there are people who deal with theoretical biology who have made progress in this area, but it's beyond my pay scale, I can tell you.
Richard Owen, he founded the Natural History Museum in London, didn't he?
He did indeed.
Yes, yeah, he did.
No, that's absolutely correct.
Fantastic.
He was based in London. And actually, the irony is that, if I have my history correct, that the Natural History Museum, of course, was an offshoot of the British Museum. And at that time of Victorian prosperity and confidence, I hope we return to those times in one form or fashion. That's my own opinion. And not as a Victorian, but just full of optimism and the sense that there's a world worth living for. Sorry, I go off into propaganda. With regard to the foundation of the Natural History Museum, amongst the people opposed to it, oddly enough, were Charles Darwin and Thomas Henry Huxley. But this is sort of political infighting. I mean, none of them would have disputed that museums are good things. But even so, it was Owen, as I understand it, who was the driver for the Natural History Museum.
Yes. Gosh, and the whole history of evolutionary biology, including your history of the sort of the late 20th century and through this one is very exciting too. Just some of the things you're referring to there do show up in a book you edited, which I thoroughly enjoyed, called The Deep Structure of Biology. And you mentioned extraterrestrial life. And it seems not only from yourself, I've heard a lot of biologists say this, that if there is life on other worlds, it's probably for these reasons to be quite similar to us, or to life on Earth, at least. Is there a sense in which nature is constrained? I know that's a fairly controversial question, but in terms of the deep structure of biology, is life constrained by avenues of success?
Well, I would argue that. And others will not agree with me, and that's, as a scientist, one actually is very pleased with this. But yes, I think the nature of evolutionary convergence on this planet is sufficiently compelling that an Earth-like planet, and we have reason to believe that the numbers in this galaxy alone are staggeringly large, of which a significant number will lie in the so-called habitable zone, where, in other words, they don't fry like Venus or freeze like Mars, but in a zone of relative comfort. And there are various twists and turns in this sort of story. But as ever, one tries to keep one's mind open. And, for example, there have been a number of papers exploring the possibility that instead of using carbon, forms use silicon. And actually, that carbon overall, I think, wins hands down for most cases because it forms long, flexible chains. And unlike silicon, which is less good at that. And the other problem with silicon compounds at room temperature is quite often they have a habit of exploding. So that's obviously not a recommendation. Having said that, though, it may be that in planets at much lower temperatures, it could be conceivable that actually a silicon-based life form, although life would be pretty lethargic, would be a viable alternative. So as ever in science, you've got to keep your mind open and just say, oh gosh, well, when it comes out. And in parenthesis, and perhaps I can mention this because I'm so interested in this area, very recently, and of course the jury is very much out here, there was a dramatic announcement of what appeared to be basically this first evidence for extraterrestrial life in the form of a exoplanet, I think about 130 light years from here. And the atmosphere was interrogated, if you like. And the investigators concluded that there was a molecule in that atmosphere, which on this planet is a dead ringer for planktonic algae. And if you really want to know all about it, it's called dimethyl sulfide. And the great thing about this is, actually, when I read the paper, I thought as a biologist, there's something I don't quite agree with here. But the really interesting thing is, some weeks later, another group of scientists produced a paper not yet peer-reviewed, which actually casts some reasonable doubt on this interpretation. And it says these other people are not wrong, but here are several other interpretations seem to be just as valid. And if you're going to teach science, that's such a good way of doing it, not to say people are right or wrong, but to indicate where the data might in fact be reinterpreted. So my own guess, and it's no more than that, in fact, this supposed example of a detection of an organic molecule and so evidence of extraterrestrial life will not be correct. But it's very early days, and of course that's just one planet out of hundreds of millions. So one's not going to say, well, there's no life out there. But in Life Solution, the subtitle of that book was Inevitable Humans in a Lonely Universe. And in my most recent book, which is dealing with sort of evolutionary myths, I return to this question of whether extraterrestrial life in fact exists. And my own conclusion, paradoxically, is that there isn't anything there at all. But that's a very mad thing to say.
Well, I mean, it's Fermi's paradox as well, obviously. If there's really intelligent life out there, it probably would have found us by now, and there's good reasons to think so. Outside of extraterrestrial life and life on other worlds, which we'll be talking to plenty of guests about in the near future, is there anything else you're really excited about in terms of your field? Any other discoveries on the horizon or big questions?
I'm not. What a disappointing reply. No, not especially. No, I mentioned I was in Toronto last week, and I was looking at some beautifully preserved fossil fish, and I can't give you any details about it, but it seems that it might actually throw some light on some really important developments in the later fish, which actually are one of the key stepping stones to ultimately coming onto land. But the fishing question is in its own way gratifyingly primitive. I spend a lot of time at the moment, also more probably in the evenings, but I recently came across a book by, and I hope I remember his name correctly, called Bernardo Kastrup. And the title of his book, I probably don't have it exactly right, is Why Materialism is Baloney. Right. I highly recommend it. It's not too technical, but the reason here is that ultimately in evolution, amongst other things we're interested in, is the evolution of the nervous system, and that is possibly convergent, and certainly in other sort of details like the evolution of large brains. They have evolved a number of times, as we see in the crows and the parrots and the dolphins and the chimpanzees. And also, in parenthesis, a good part of what you need to make a nervous system involves molecules which evolved long before there were any animals. So the building blocks of a good part of the nervous system are already there. So fine and large, that's all very interesting and pretty technical. But on the other hand, behind all that is this question, well, two questions in a sense, of you and I talking, we're using language, which we take for granted, but actually, as any scientist should do, if you step back just a couple of feet, language is extremely peculiar. We take it for granted, but animals do not have language. They communicate, but they don't speak. And then that, I think, has some connection to the hoary old question of consciousness. So back to the materialism is baloney. Beneath that substrate of, if you like, day-to-day biology and day-to-day evolution, there are profound questions as to how we think, how we conceive of abstract matters, how many mathematicians will tell you that they don't invent what they come across, but it's discovered. And actually, interestingly enough, you come across exactly the same thing amongst many novelists. And I've read a number of accounts fairly recently where the novelist suddenly finds to his or her surprise that some character wanders into the novel and suddenly takes over. And I think we probably don't have a lot of time now, but I'll give you one such example. And I'm not sure which of the books by Evelyn Waugh it was. It might have been Vile Bodies. Any case, there's a particular character in this book. And when the book was almost finished, Waugh suddenly realized that this woman, this character, was an alcoholic. And as soon as he realized she was an alcoholic, suddenly the rest of the book fell into place. Somehow this invented fiction somehow had a reality. And I can't help but think, although I don't think authors, in a sense, make other worlds, I suspect, in fact, our powers of imagination, and we see this in the great authors I admire enormously, Charles Williams, C.S. Lewis, J.R.R. Tolkien, in their different sorts of ways, open new sorts of vistas, which are not what science does, but suggest that the world around us is far, far different than perhaps your ordinary materialist, bless them, would think.
Yes, and this is just so fascinating because it's another example of the interdisciplinary nature of what we do. Philosophy meets biology, and and where things like language and consciousness can open up so much in terms of our understanding of the development of life and also the uniqueness of ourselves. And I know we've had many conversations about the nature of consciousness. I just wonder, I have to ask you here, in brief, do you have any thoughts on the origin of life itself? I know it's a long way before the Cambrian and Ediacaran, but...
Well, I can answer very, very quickly, or even more quickly. The simple answer is no. But that in part is because although I did read fairly extensively into the topic and actually talked to a number of people about it when I wrote Life Solution, I've not followed the literature at all. My understanding is that in terms of, if you like, precise chemistry in laboratories, a number of significant advances have been made. The question there, of course, is what relevance, if any, do they have to the Precambrian world, which is, very variable chemistry and all sorts of other things. And these may be, if you like, the pointings towards, how these cells self-assembled. I really have no view. I mean, one possibility, which is being mentioned by a few quasi-theologians, is actually per se the origin of life is just a complete fluke, and you have to have a universe the size of the visible universe simply to throw the dice so many times that once or twice they just happen to come together. Now, most scientists would regard this, and quite rightly so, as deeply unsatisfactory, because in principle we know perfectly well what the atomic structure of life is. We know perfectly well that a good number of the compounds which are the precursors of cells, the building blocks, if you like, can be formed in unexceptional conditions. We call it organic chemistry, but it's not organic in terms of life. And at least some of these compounds we know from the investigation of a particular group of meteorites these organic compounds are present in considerable abundance. And this also applies not only to meteorites, but almost certainly to comets as well. So in principle, with those building blocks and with a propitious environment, then life should be universal. And it may simply be that there's, a set of bottlenecks which you have to go through, which are perhaps to some degree fortuitous. But I think almost any scientist would sort of say that they don't doubt life has a natural origin, and that would be my default position, certainly. But if I was asked to give you the details, I simply can't. I can tell you what the building blocks are, and I can tell you what a cell is, and I can give you some hypotheses as to how they came together. There are 5 or 6 perfectly reasonable hypotheses around, but actually convincingly showing step by step in the way that, if you like, Darwin insisted, I believe has yet to be achieved.
But this is the immense paradox of life. It seems to have come about very, very early on our planet, when our planet was very, very inhospitable and conditions were really quite unpleasant. And all the ingredients are there readily available. And we sort of seem to know what it is, and yet we can't find it yet anywhere else. It's a beautiful paradox. Still one of the great unanswered questions
Mm.
in philosophy of science. Thank you so much for your time today, Professor. It's always a pleasure talking to you. And I can't recommend your books highly enough. And I hope those listening, young and old, take them up and get interested in ancient life for themselves.
Thank you very much, Sam. It's a pleasure as always to talk. Many thanks. Thank you a lot.
If people want to know more about you, where could they go?
Oh dear. Well, I don't run a website, I'm afraid. With respect, I would simply say that if you want to know what I'm thinking about, then my most recent book, called, I think, from From Extraterrestrials to Animal Minds. It gives a sort of, it's got 6, if you like, evolutionary myths, and one of them deals with the uniqueness of humans, another one deals with convergence, another one deals with the question of extraterrestrial life. And it's been out for a couple of years, and in its own way, although it's a bit of a hugger-mugger, I'm very pleased with the book, as any author should say of his own product. In fact, I lean forward and say it's absolutely first rate. Well, no, it's not, of course.
Excellent. It certainly is. Thank you very much, Professor. Much appreciated.
Thanks again.
Thank you so much for watching. Don't forget to like and subscribe. Stay tuned for more amazing conversations with incredible researchers who are changing the world we live in and driving humanity forward. Feel free to check out my Instagram at polymath_Sam, or go to my website at www.sam-mckee.co.uk.